It heard me braiding it, and it just did. That's great. Hasn't done that all day. Had to janky it over. What numbers did we do?
36 to 54.
All right, number 36. 1.9035 times 10 to the 6 and 1,903,500. 38. 2.4 times 10 to the 8, which is 240 million. 40. 8.55 times 10 to the negative 8, which was 0.00000000855. 42, 1.5 times 10 to the negative 4, which is 0.00015. 44 is 9.288 times 10 to the 8th, which is 928,800,000. Excuse me. 46 is 4.7 times 10 to the 9th, which is 4,700,000,000. 48, 5.9 times 10 to the negative 6, which is 0.0000529. 50 is 2.5 times 10 to the negative 5, which would be 0.000025. 52 is 4.3 times 10 to the 10th, which is 43 trillion. Did we do 54 as well?
Yes.
Awesome. 54A is 91,400,000, which is 9.14 times 10 to the 7th. 54B is 94,400,000, which is 9.44 times 10 to the 7th. 54C is 3.3%. What questions do we have on those? 54. 38. Okay. Do you have work done on 54? Did you try it?
I tried it.
Okay, then I'll answer it.
Without like 2 zeros at the end of each.
Okay. Distance between Earth and the Sun varies throughout the year. The Earth is closest to the Sun in January when the distance is 91.4 million miles. In July, the distance is greatest at 94.4 million miles. Right, 91.4 million in both standard form and scientific notation. Where did we have problems on this problem? I'm a little confused. Because this problem is easy. Where are y'all confused? So I can actually help answer like the issue with it. You got this part or no?
No, I forgot to do that.
Oh, okay. So who knows?
Times 10 for the,
You did 91.4 times 10.
no, I didn't, 91.14 times 10 to the 91.4.
Well, remember to do proper scientific notation, it has to be to the right of the first non-zero number. So it's got to be 9.14, right?
So we'll give me the
Times 10 to the 1, 2, 3, 4, 5, 6, 7. Good. It's not a dumb question. I just want to make sure I'm answering the right question.
How many exponents do you add then? On the that's what it goes with the exponent.
On the what number were you talking about?
38.
38.
What did you add the exponents?
You would subtract the exponents because they're like bases divided. So it would be 3 minus negative 5, which would be positive 8.
For some reason, I added a bunch of them.
Like 36, you would add them, right? Because it's like bases multiplied.
But like on 46,
Mm.
stuff like that.
Yeah, you got like bases divided, so you would subtract the exponents there. Mm-hmm. You what?
I need some paper.
Well, you better tell your parents.
What?
That's the paper you need. How many sheets?
2,
Now you say thank you.
3, 7.
No, you're mean.
I need to.
The guy's giving you paper and you're just sitting there like, oh my gosh.
Can you do 54C?
Yeah. We can do 54C, sure, why not? So, you would have gotten, for A, that, and for, no, don't do this yet. Don't jump ahead. For B, you would have gotten this. Yes? Correcto. For C, it tells you what is the percent increase in distance from January to July round to the nearest tenth of a percent. So it's been a while, I know, well, a little while, but we've talked about how to find a percent increase. How do you do that? You do that. You subtract the final minus the initial and you divide it by the initial one. So let's do it real quick. 9.44
I don't even remember that. And then you said that.
times
Or
10 to the 7th minus 9.14 times 10 to the 7th over 9.14 times 10 to the 7th.
That's 17 on the top.
That's why I wrote it wrong.
You were like, wait a minute. That's why you got to engage the brain. Don't just copy what I write. You're not remotely unique in doing that. Lots of people do that. Okay, now what? Well, we should subtract first, right? What is 9.44 times 10 to the 7th minus 9.14 times 10 to the 7th?
0.30.
No. But kind of.
Job sort of.
What'd you say?
9,134.86.
No.
Yeah, that's what it would be, bro.
Oh.
Point three.
Something like that.
I got 30,
Something with the third, I guess.
33.
We're getting all kinds of things happening here. If you did it by hand, the long way, what's going to happen? You're not going to move the decimal anywhere. You're just subtracting. Minus.
That's right.
I didn't think that was
That's
right.
right.
That's what I thought. You should have said that. I told you to say that. Yeah, I just wrote it.
So 3.0 times 10 to the what?
Eight.
Seven.
8. 6? Oh, I was looking at
Which makes sense. You could have done all of that like from this. These are the same, they're going to go away, which means the decimal point's going to move over, which means that's going to go down by 1. 4 minus this, y'all were getting the 0.3, right? It would be 0.3, 0.3 times 10 to the 7th, right? And then to get correct scientific notation. So y'all were like all around it in your head. You just killed a bunch of zeros because they were ugly or something.
No, just divide that.
3 divided by 9.14 is what? It's like about a third, right?
No.
0.3.
0.33. Boom.
Now what?
You move the decimal over.
Move the decimal over once. So 3.3 times 10 to the negative 2. Now, how do we write that as a percent? Well, y'all are used to doing it like turning this back into standard notation. Turning this back into standard. How do I write 0.033 as a percent?
Move the decimal.
Yeah, which is, yeah. You don't need a calculator for that. 3.3%.
Oh, I got an error.
You got an error.
I just,
So, which is a percent
no.
3.3%.
of the sun?
Of the change in distance for how close the Earth is to the sun. Which is, when we're talking about these types of sizes and distances, you're talking about a very small change. Very small change.
100% change.
No, 100% change would be if it went from 0 to whatever it is, 91 miles. Trying to understand your shirt.
Oh, it's a Catan shirt. One of the variants.
Oh, it is a Starfarer. There's not sheep in that game, is there?
No, it's just like, because like sheep is like the.
Have you played Starfarers of Catan? That's on my list to play at BGG this year. I've been meaning to play it for a while. I've heard that one's actually pretty good.
I actually have it. I mean,
And lots of I've heard that it's good from people that would agree with me that Catan is meh.
I mean,
They
It's a fun game, man.
I own a copy.
Catan is fine. It takes a long time. You don't even know. You haven't even played long games if you think Catan takes a long time.
I have no speakers.
So my issue with Catan is it's half a good game. Yes, ma'am.
I have no
When it's a decrease, you told them they don't have to put the negative
Right.
sign in front of it? Okay, I just wanted to make sure, because they just yelled at me about putting the negative sign in front of it, and it's like, you said it in the video. I was like, I watched it at 2 times speed. I didn't tell them that. Okay.
Bye.
I have no speaking to this because I am a Catan maniac. Like I'm obsessed with it. I have it.
Yeah.
So,
I don't care if people like Catan. That's totally fine. But Catan is fine. Catan to me is half a good game. Like the first half of Catan is really fun. Like where we're trying to buy up stuff and get things and try to get things arranged just right, and it's fun. And then the second half of the game is just kind of like, okay, eventually somebody's going to get another point. It's just like we're here sitting here, whatever. That's my issue with Catan.
that would be who you're playing with.
No, it wouldn't be. That's exactly how Catan works. That's exactly how Catan works. Is once the stuff is kind of set, you're kind of set on a path, right? All right, there's it's whatever else. Now, group matters, and you can play with crappier people and whatever else. Group definitely matters, but so my problem with people like you who have only played Catan is that they've only played Catan. Like they haven't played like so many other games that are so much better. That there are so much better resource management trading games than Catan. So much better ones. But that's not always true because my brother-in-law, his favorite game is still Catan, board game. And he has definitely played a lot of games. So it's not always true.
Rounds.
I also do. My second favorite game is Ticket to Ride, and I don't want to say what.
That's also like you need to get out the mainstream, bro. Find any games that you can't find at Target. Find games that
I
are.
bought all these online.
Well, yeah, I know. I'm just saying, you need to play games that you can't buy at Target.
You heard of a Plunder?
You like it.
I've not played Plunder, but it looks pretty good.
My fellow played it the other day and said it was okay. So I was like,
Nice.
give it a go.
Yeah. Yeah, I am a nerd. It's fine.
Like, if I had to give like a scale of 1 to 10 on Starfarer, I'd give it like a solid 7.5. It's pretty good.
I haven't played it, so I can't tell you yet what I think about it. But it is on my list to play at BGG this year. I fully intend to play it.
Board Game Geek,
Board Game Geek Convention. Yes.
where you had it
Yeah. You should tell your family they should go. Of course, there's probably some stupid Spartan thing or something. It's in Dallas.
What month is it?
May.
May. Oh.
What day?
It's at the end of May. Let's see, do I have it on my calendar? Let me look.
20.
It's too far away.
Through the
It's just
30th. 2 days, yeah.
Why can you stay on
On
the
the 30th.
It is the 22nd through the 26th of May this year.
Well, we would have gotten to Spartan the weekend before.
See, you're free. You should tell them. They should get tickets.
I think at that
Okay.
time I'm at a different thing, most likely.
Oh my gosh, you're at a thing.
Final spring.
BGG is the best.
Like,
It's the best convention that honestly one of the best vacation things I've ever done. Because most vacations kind of feel like more work. BGG is just let's go have fun and play some board games. It's great.
What do y'all like actually like?
Unless you don't like board games.
Well, we play board games, lots of board games.
I've never really been to a convention, so I don't know.
Well, BGG is different than like a Comic-Con or something. There's not really like panels and stuff there where you go sit and listen to people and what all these things. But no, it's a bunch of people that like playing board games, playing with other people that like to play board games.
That sounds awesome. Harvard. You say that.
Okay, there are 2 parent functions.
Parrot.
What do you mean finally? It was like 2 minutes. Calm down.
Did you just, like...
I just responded to it, yes. Did I just note it? No. But I was running my mouth, so I just responded to it. I did say that's what we're going to do, but I guess you weren't listening.
Take too long drawing them. And when I finish drawing them...
Well, you need to draw faster. They don't have to be that perfect. You got this.
Everything is perfect.
No, that's not true. So, the way the equation looks for both of them is f of x equals a times b to the x. The reason why exponential is not the only type of function that does this. Logarithmic functions also do, because they're the inverse of exponential, so it makes sense. But most functions in algebra live in a single parent household. Most of them only have one parent. But exponential have 2 parents, and so do logarithmic. Like the linear parent function looks like this, right? Yeah, we've been seeing that for a long time. Right? Exponential parent function looks like this. If a is greater than 1, well, greater than or, what does it say? Is greater than 1, and b is greater than 1, then the parent function looks like this. There's a few key things.
You wrote 0, but you said 1.
I meant 0.
Okay.
Didn't I mean 0? Yeah, I did, but I meant it the other way around.
Okay.
Yeah, that makes more sense. Okay, there's a couple things that go on in this graph. First of all, there is a new thing that you've never heard of before, probably. There is an asymptote. Asymptote. There's an asymptote all along the x-axis. Don't worry, I'm going to write it and we're going to explain what it means. This is an asymptote. It's got a cute little silent P in it. Asymptote. What an asymptote is a line somewhere where the graph, the function, gets closer and closer and closer and closer to, but it never quite gets there. Okay? Yeah, I know. Lonely, sad. Okay. It also, the parent function, in the parent function, if there's no transformations happening, it also crosses the y-axis at 0, 1. When these conditions are true, it gets closer and closer to the x-axis going this way. So it's going down, kind of slowly. And then on this side, it looks like this. That's what it looks like, juice like that.
We only have one color.
You don't have to match the colors.
I just picked a color.
No, you're totally fine. I'm not yelling. I'm not saying anything. It's gonna be okay. If I was doing only one thing in a color, I would do this one because otherwise this one's gonna be hard to see. This one you can just do black. That's what I would do if I were you, but you can do whatever you want to do. But if I was trying to make my notes legible, that's how I would do it. Now, if A is greater than 1, no. A is greater than 0, so it's positive, right? And B is between 0 and 1. So this, I just said this out loud. How would you say this out loud? I just said it, so if you want to repeat what I said, that's fine, but since you weren't listening, what does this mean, A being greater than 0? What's another way to say that? What numbers are greater than 0? What numbers are not greater than 0? Negative numbers. So numbers that are greater than 0 are positive. Great. So A being positive, right? Great. This one, B is some number bigger than 1, right? B, this number being raised here. This one, what would be another way to say this? No, it's between 0 and 1. What numbers are between 0 and 1? There's not nothing there. Fractions. Fractions, 0.5 and 0.3, etc. There is an infinite number of numbers between 0 and 1, but they're all fractions, right? Yeah. So if B is a fraction, then it looks a little bit different. It still has the same asymptote that's pronounced asymptote because the P is silent. Has the same asymptote. So it still gets closer and closer and closer to the x-axis, but it never quite gets there. Never gets down to 0. Right? But the graph this time looks different than that. Because the graph gets closer and closer on the positive side. It still crosses the y-axis at 0, 1. That's still true. Oh, I covered up my blank mark. We should label that over here, yeah? This is at 0, 1. So it gets closer and closer on the positive side. Goes over there. Now, we name these two parents. These parents have names. It's not Charla and Bill, because that wouldn't make any sense. But what it is this is exponential growth on this side. And this is exponential decay. So let's pause and put a pin in it before we do an example. So there are lots of real life situations where the data matches an exponential function. fact, more than linear functions. There's not a ton of linear functions in the real world, but there are some. What is something in the real world you can think of that would be exponential? Make a guess. No, there's nothing, well, there's nothing really about you that's exponential unless you're talking about the bacteria colonies living on your skin, because they tend to grow at an exponential rate. That's true.
Okay, in Minecraft, when you said it takes speed to 1,500.
No, it'd still be linear, because it's still growing at the same rate.
But it's extremely fast.
Acceleration?
Let me, no, I definitely wouldn't be exponential unless we're talking about like an absurdly crazy vehicle. I've kind of already given you a hint, and somebody said something about one or something. I've kind of given you a hint. So if I have whatever this animal is, if I have some pigs, and I have a couple pigs, if I have a couple pigs,
Oh gosh.
and then they have more pigs, and then they have more pigs, and then they have more pigs. Population and absolutely can have exponential growth. We talk about that with rabbits, right? They spring up like rabbits. That's not really what happens, although their gestation period is short and they have large-ish litters sometimes. So money is a great one. Before we talk about money, because money we're going to camp out at for half a second, because I always do, because here's the deal, boys and girls. You don't learn this book. I've talked about this before. This is relevant. This is good. This is not like me off topic. This is important. This is on topic. You do not learn this. I lost my place. Because of this. You don't take algebra because of algebra. It has nothing to do with why you're doing algebra. You learn algebra to build part of this. That's why we do this class. However, and so when people are like, oh my gosh, when am I ever going to use this? Never is the answer. You're never going to use this, most of you. You're never going to use this ever in your life. That's not the point. It has nothing to do with it. And most of the time when people are whining such stupid nonsense as that, they just don't want to do the work. They don't actually care about the answer. Now, however, one of the things that I'm going to talk about today and give you a micro speech about is compound interest. How old are you? 14. 14, great.
Oh, yeah,
You are 14. What right now is typical retirement age?
Like 60s.
65.
Okay.
We'll go with that.
So
So, when you invest money at compound interest, and we're going to see this when we actually do some examples and actually do compound interest formulas here very soon, but it's worth talking about sooner rather than later. The most important variable is time, because it's the one that goes up here in those formulas. How many years are between here and here?
51.
51 years. 51 years. Now, when you invest money, it takes compound interest, which is exponential. What do you notice about this graph at the beginning of this graph? The beginning of this graph, like from here to here, is your, in this case, money growing very fast. Like from right here, it's not growing very fast. It starts like this, and then it gets more, and the longer, and once you get out here, it's growing a lot. Now, we're going to do it with a calculator. I'm going to teach you how to do it by hand soon. If you're welcome to mess with your calculator, but I am going to like type in compound interest calculator and then shove it in a website. But if you want to try to punch some numbers in, you can do it. Okay. If tomorrow you put in $100, $100.
No.
That's it. Any of you in this room can make $100, like easily. Gemma makes that on a Tuesday in an hour.
I could.
Right? If you invest $100 and we leave that money in for 51 years, we're between 1 and 50. Just kidding. Okay, how about 50? That's fine. Why not? And we get a 15% rate of return for that amount of time, which is definitely doable. I don't care what some whining adult tells you. That's not, they're confused and ignorant about what they're talking about. You can definitely get 15% over the course of 50 years. In fact, you can probably get more than that. But 15 is easily doable. And you don't put any more money into that bank account. Just $100. 15% compounded annually, we'll say. We don't really care about monthly and annually because it doesn't make a huge difference. Your money with just $100 tomorrow when you retire will be $170,000. Now, if you instead tomorrow put $1,000, so save $1,000, any of you could make $1,000 in a year. It could happen. You could do it. It might take some work, but you could do it. Put $1,000 in there. It would be, after 50 years, $1.5 million. Now that's cool, but you know what's the real moral? If I change that and we instead wait 20 years to start, and we only invest that money for 30 years. So we change that one variable. We still put in $1,000, but we do it for 30 years. Instead of being $1,700,000, it's now $87,000. That's a pretty big difference. So the point I'm trying to make with you, and it matters. So what the whole spiel about how you don't learn algebra for algebra, that's true. However, your real life lesson today is start investing some money now. Don't wait. Because the longer you wait, the more you can't recover. You can't go back and like recover old interest from when you were a kid. You just can't make time back up. It doesn't work that way. Okay, let's continue talking about exponential functions. Okay, let's do a graph this function example. You look at your homework before yeah, nice. Good. What? Oh my gosh, I have homework. We're going to do two examples. We're going to do an easy one and an ugly one. Sounds like a great idea. Graph. Y equals 3 to the x. Which parent function does this one go with? Growth or decay? Growth. How do I know it's growth? No, it's not because of the negative. Yeah, because it's greater, because b is 3, which is greater than 1. So the parent function looks like this. So that's what this is going to look like. So here's what we do. You ready? Yeah. We're going to find a table of values. And then we're going to plug points and then connect the dots. Think you can handle it? So let's plug in -2, -1, 0, 1, 2. Wait for what? Okay. That's so sad. I'm sorry. I was trying to decide what I was doing. Okay, so What's 3 to the negative 2? Put your calculator away. You can do it without one. What does the negative in the exponent do? Change levels. So this is 1 over 3 squared, which is what? 1/9. I'm not saying you can't use your calculator on these. I'm just saying you don't necessarily need to. What is 3 to the negative 1? 1/3, right? What's 3 to the 0? No. Anything to the 0 is not 0. It's 1. What's 3 to the first? 3. 3 squared? 9. Let's go chicken nuggets.
And these numbers are just made up.
These numbers I did pick at random. We're gonna narrow some things because I have decided that's what the brain pause was a second ago. I'm gonna teach this like I want to teach it instead of the way the book teaches it. I'm gonna teach it like I would teach it if you were in Algebra 2. 6, 7, 8, 9. And I promise that it's better that way. 1, 3, 2, 9, and these little numbers. Grand. To be clear, if this problem was on a test or quiz or whatever, this and this are the answer. If it's just this, it's not good enough.
How did you graph? Okay.
I just connected the dots and then did it like the parent.
Where'd you get the points?
These numbers I pulled out of my head.
They'll tell us.
How did you graph that? How would you graph that?
Like that. Okay.
Like, what are the points?
Where would
These
you get them? Where would you get them?
are the points.
So,
Where would you get them?
How,
would you graph?
okay.
Like, would you go down to?
No, there's no slope. It's not, the parent function doesn't look like that, it looks like that. So you draw the dots, which we did. We did a dot up here, we did a dot up here, we did a dot over here, and then you get some that are getting closer and closer to 0. And then you know that it's got this curve, and so you just connect the dots in a curve.
He's saying, where will we get the numbers? in
Yes,
this
like, how did you get the?
Are you asking about the left side of this table or the right side of this table?
Like, where did you get the points? What, like, from the?
I'm about to throw something through the wall. Quit saying the same thing over and over. Answer my question, and then because what I'm trying to do is I'm trying to figure out where you're confused. And if you'll answer my question, I can do that. Are you asking about where I got these from or these from?
Neither.
This. Okay. All right. Listen to my answer because now I think I'm answering your question. This is a point, and so is this, and so is this, and so is this, and so is this. These are all points. This is x, y. Yeah. This is like, for example, this is 1, 3. Hey, I didn't mean for that to be painful. I just got to get to to figure out where are you confused? Well, we got there. We did it. Oh my gosh, that was the lamest fist bump ever. Okay, let's do a more difficult one.
Okay.
Oh my gosh, nerd. Live. I was just seeing if anybody was saying words.
Is anyone saying?
Nope. No words. No watchers either. There was at some points a watcher, but they're not there anymore. Okay, so let's do a more difficult one. But no, actually, no, stop. Put a pin in it. Because I already decided I wasn't going to. Okay. I'm going to teach you something that the book doesn't teach you. I think I know why they don't teach you. I think they probably save it for when they talk about quadratics, if I had to guess. But the sooner we learn this formula, the better, because it's forever. Every time we learn a new type of function and graph a new type of thing, it's the same thing, and it works the same way. So, we already talked about what the parent function is. This we're going to call transformations of the parent function. Transformations. What does the word transformation mean?
Turning.
You can't define the word with a word. What does the word transform mean?
Turn into something else.
Yeah, changing it, right? So these are ways that we can change it. We better use the letters that we'll see. One of those you're not going to see this year, if I had to bet any kind of money on it.
Yeah, you better give me some $50.
What, $50?
Yeah, one of those you're not remotely going to see on this in this lesson. On exponentials, there's not going to ever change. H is not going to change. It's just going to be at 0. H is going to just whatever. We'll go ahead and put it for completeness sake, but we're not going to mess with H for now. Right. For us, it's not going to be there. Okay, so all of these letters do something to the graph. Okay, this one, A, is a dilation and or reflection. What does the word dilation mean? Where all have you heard the word dilate?
Your pupils,
Pupils, absolutely. What if I said your pupils were dilated, what do I mean?
they get bigger.
They get bigger. So a dilation is either a stretch or a compress. So it's either stretched or it's compressed. Reflection would be what?
An image mirrored back.
Right. So reflection would be flipped down. So if A is negative, then the exponential parent function, exponential growth, will flip down and it'll look like this. If it's greater than 1, it stretches. If it's less than 1, it compresses. Okay. Now, the K is a vertical translation. Okay, so what does the word translate mean in this context? It's a little trickier. No, not Spanish to English. Okay, so translation in this context is a movement from one place to another. Vertical is what?
Up and down.
Up and down. So K, if K is like plus 2, what's going to happen to the parent function?
It would be minus negative 2.
The graph is going to move up. Okay. Now, H, I would make a bigger deal out of H, and we would talk about the fact that it kind of goes opposite what you expect and all that kind of stuff. But we're just putting it in here for completeness. We're not going to talk about it anymore for now. It's a horizontal translation. Okay. So those are that pattern is going to be true no matter what the function is. This actually works for a linear function as well. The slope is the dilation or reflection. It stretches or it compresses. And then the K, which we use a B for, it moves it up and down, right? So it even works with linear. Okay, so this pattern always works. Or did you have a question?
What's B and X?
X is the variable, right? X is just the variable, yeah? B is which parent in this context? B is not really, well, it is and isn't. And B is one that we don't really talk about in Algebra 2 either. But it's which parent in this context? X is a variable. It's the independent variable, in fact, just like it always is. Wow, that's a dumb looking question mark, but it's fine. He probably has a great personality. Okay, let's do one more example, give you some homework, and then kick you out of here.
What was the X on top?
We'll put on here, but we don't want to.
Okay, so I've said the answer to your question 4 times, so somebody else maybe answer it. What is the X?
The variable.
It's the variable, it's the independent variable. What?
There's 2 variables.
Yeah, f of x and x, just like always when we graph things, right? There's got to be 2 variables, unless there's 3, and then we're graphing in 3 dimensions. That definitely won't happen today or in this class. All right, let's graph this one. Y equals -2 times 3 to the x plus 5. Okay. So we're really pretty much going to do the same thing we did on the easy one. We're going to pick some numbers, solve for the y part, put the dots, do the things. But it's helpful if we think about what I just showed you. So let's start figuring out what this is going to look like and how it's going to change from the parent. First of all, which parent are we talking about, growth or decay? We are talking about growth. Although, we should totally change this example, that way we get one of each. We're talking about decay. Of course, we were always talking about decay, always. We never were talking about growth. I don't know what y'all are talking about. This is decay, right? So, this is what the parent function looks like. How does our graph change the parent function? What all things change?
Because it's a negative, does it flip it?
It flips it. So it flips it over, right? So instead of being like this, it's going to be like this, right? What else changes? Did you know that 2 is not 1? That's true. 2 is not 1, which means, what I'm getting at, what does that 2 do? The negative flips it. What does the 2 do? It is just there, but what does it do because it's there? It dilates it. It stretches it by 2. What does that 5 do? A vertical translation, so it moves up by 5. So, when we're going to do our graph, normally on the parent function, where is the asymptote? It's normally, just right at the x-axis. What's going to happen to the asymptote on this one?
It's going to be on the y-axis.
No, it doesn't flip sideways. It doesn't become logarithmic. Why did I dot that line? Because I was talking about asymptotes. One of those numbers moves the asymptote. Which one? -2. -2 flips it over and stretches it out.
5.
The 5 moves the asymptote. So which direction is the asymptote going to move? Up 5. So the first thing we could do is go up 1, 2, 3, 4, 5, and dot in an asymptote. If I was just gonna like YOLO at this point, it said it reflects down. I could put a dot right here and just go like, it looks something like that, right? And that's what it's gonna look like. So when we get some points and we get some numbers and we get some dots, that's what we're expecting, right? So let's pick some things. What numbers do we want to put in for x?
0, 3, 5, 6, 7, 8.
How about we pick
Same numbers.
like 1 or 2 over here and like 3 over here, right? Because these ones it's just going to get closer and closer to the axis. So let's pick like -4, -3, -2. How about -4, -2, 0, and 1. That's easy money, right? What is 1/2 to the negative 4? What does the negative do? Change levels, so what's 2 to the 4th? You can use your calculator, I'm not saying you can't. Just let's think about our properties while we're doing things so that we can know things. Two to the 4th is 16. What's 2 times 16? Negative 2 times 16. Negative 32. Plus 5. Negative 32 plus 5.
Negative 27.
That's the one.
Okay.
Great. Let's do another one. Another one. What is that? Oh, I erased that. Negative 2. So what is 1/2 to the negative 2? It flips it over, so it becomes 2 squared, which is what? Are y'all punching 2 squared in your calculator? Calm down. It is 4. So negative 2 times 4. What is negative 2 times 4? Negative 8 plus 5. What's 1/2 to the 0? 1. What's 1 times negative 2? Negative 2. What's negative 2 plus 5? 3. So, the y-intercept,
Forgot one.
I didn't forget one. I was just like pausing for a second. The y-intercept is at 3, which is where we said it was going to be. Imagine that. Wowzers. What's 1/2 to the 1st? What's 2 to the 1st? 2. So what's 1/2 to the 1st? 1/2. Negative 2 times 1/2. That's 5. What's negative 2 times 1/2? Negative 1. Negative 1 plus 5 is 4. Imagine that. What is our number going to get closer and closer to but never quite get there? It's going to get closer and closer to 5 but never quite get there, right? So this is all making sense. So, negative 4. Let's try. Let's see whether it'll go to 5. If I plug a 2 in there, negative 2 is 1/2 squared. What's 1/2 squared? 1/4. What's 1/4 times negative 2? Yeah, so negative 1/2. What's negative 1/2 plus 5? 4.5. 4.5. Let's go crazy. Let's get a little bit crazier. Let's just to prove my point. Let's do 1,000. What is 1/2 to the 1,000? Put it in your calculator. Go for it.
I don't think you're into that. Surprisingly. I keep topping everything on.
0.
500.
It's going to be 0 point something.
Oh, that's fine.
Yeah, it's a rounding error in your calculator. So it's some super small number. Some itty bitty number. Itty bitty number. So this is going to be also an itty bitty number. So it's going to be 5, or it's going to be, excuse me, we're subtracting. It's going to be 4.9999999999999. You didn't. Your calculator is just confused because of rounding error. If you put something more reasonable, like put 100 in there, maybe that'll make your point, my point better.
7.88860.
Times 10 to the something, yeah?
Negative 31.
Yeah. So super tiny, right? Super tiny. So this is still going to be 5.99999. So it's going to get closer and closer. Yeah? Never get there. Yes? Okay. Okay. So we put the points in. We do the things. There's the thing. Now your homework is Yes.
Darn it.
It's one thing of homework. You're going to be fine.
Oh, yeah. There's still 2 through 6.
It's like a missile, like.
Page 427.
Hey, 427.
Numbers 2 through 20 evens.
You're so nice to us.
Omit 8.
What's that supposed to mean?
Means don't do 8.
Not do it. Boom.
What's wrong with the 8? He wants
Everything.
I don't like that problem right now because you don't have graphing calculators and I don't really want you to just YOLO it by hand.
Another question. Why do you got a calculator?
So that means you
The only class that I require a graphing calculator for, and I actually rent them out if people don't own them, is pre-calculus.